Alright, so this is video talking about the controllability. So this video is for March 24th, 2020. So in this lecture, I'll talk about the controllability for a linear system, linear time invariant system. So next lecture, I'll talk about the controllability for a linear time invariant system. So here's the definition of the controllability for linear time invariant system. So if you're given linear system with a form x dot ax plus bu, so this is a typical form for a linear time invariant system. The system is controllable, okay, if this is a condition, if for any initial state x0, okay, the initial state at the time 0, and any final state xf, okay, any final state want to reach, there always exists an input. Basically here is the use of t is my input that transfer x0 to xf in a finite time, which means this, by using the input we designed, it can drive the state of the linear system from x0 to xf. Okay, so this picture shows example what this means physically. So let's suppose that the linear system has an initial state x0, okay, which is somewhere over here, and we want to drive this state from x0 to xf. Okay, so if we could design some control input, for example, here I give two different cases. One is ut, assuming that we have one ut, they can drive from x0 to x to xf, maybe from t from 0 to 10. Okay, I can drive from the initial state x0 to xf, or you can also use ut, this is the blue line, the input, the blue one, and you also drive from x0 to xtf. So you don't necessarily have the same, you start at the same time of course, but any problem at a different time, let's say 5. So as long as you can find a 1, okay, ut, either red one or blue one, you could have even more. I could even have more possibilities going here, and this is my another ut, and for t from 0 to 20, for example, you drive from t0 to, that's fine, as long as there exists an input that transform my state from x0 to xf during a finite period of time. You cannot be an infinite period of time. Okay, so the system is called controllable. Okay, so this definition is equivalent as a following definition, which means if the system, linear system, is controllable if given any initial state x0, there exists a ut control input, a serial control input at different times, such that my xtf will be 0 for a finite time tf. So which means I want to drive this one to 0. So this is the origin. I want to drive it over here. So you always can find for any initial state, doesn't matter where you get started, you always can find something that can control input that can drive you from here to this origin. Okay, and some ut for a finite time. The reason why it's the same, because I can for the linear system I can do a change of variable. Basically, I can change the initial state as a shift, right? I can change my I can always set my tf as my coordinate frame, like the origin, because I can shift it. Okay, that's the same thing. Okay. Similarly, this linear system is controllable if is also equivalent to the statement saying that if the linear system is controllable if given any xf, there exists a use of t such that xtf is equal to xf when xt0 starting is 0 to 0, which means starting from 0. It's also always equivalent to say, hey, I'm going to start with 0 0, because you can move, you can shift your coordinate from initial point from anywhere to anywhere else as long as you do the final change. That's why there's 3 different definitions, the 3 different conditions, they are the same. So any of the 3 conditions, this is one condition, if for any single condition and any final state, there exists an input that transfer x0 to xf in a finite time, or given any x0, there exists ut such that xtf will be 0 for a finite time tf, or for any xtf, there exists a ut such that xtf is xf, one xt0 starting from 0. Okay. So any of three condition, any one of three will be okay to guarantee the controllability from the definition point of view. Okay. Now let's take a look at some example to see if the system is controllable or not. The first example says x1.t is u1, x2.t is u2. So basically you have u is u1, u2t. Okay, you can write this one as basically as x1t and x2t, which is derivative is you have the 0, 0, 0, 0 time x1t. You can write it in a linear system form plus it's 1001 time u1 and u2. Okay, I drop the t because of the limit space. So this is my A, this is my B. So we do have linear time invariant system. So if the system controllable, so since we haven't talked too much about the other conditions, so we can use a definition. So can we drive, let's say the problem, we can use, I don't necessarily have to use the first one. Okay, we can use the second one. For example, for any interstate, there exists ut such that xtf will be 0 at a final time. Let's say you start from any time, you nx10 and x20. Can I drive this? Can I design my u1t and u2t such that I can drive this one to be 0? Yes, of course I can drive it. If this x1 is 10, then you can always drive this one to be, let's say if x1t is 10, well you can just let your u1 to be negative 10, drive that one. You just take 1 second for you to drop from 10 to 0, right? The similar you can find any other state. If it's 20, you can drop it down to, just say u2 is negative 20. It still take 1 second for this u2 to drop from 20 to 0. So yes, this is controllable. If you look at another example which says x1.t is u and x2.t is u. So here they share the same u because they're same, they're equal. If you write this form, we do have x1t and x2t. Let's use black. Okay. X1t and x2t derivative, which is 0, still 0, 0, 0, 0 time x1t and x2t, plus here we have, which is 101 time u. So you do have same input, right? Is this system controllable? The answer is, for this one, is no. The reason that it's not controllable because you do have the same one, which means if they're the same, you always drop the same one. For the derivative, you always drop. For example, this one, say if you do the derivative, if you make u to be positive, for example, your x1t will increase, also x2 will increase with the same amount. For example, if you start with x10 is, this is x10, this is x20, so you do sort of parallel. Okay, so if you want to go to 0, you cannot drop both to 0 at the same time, right? Because I want to make sure this one will go to 0. You cannot find one because they can drop the same value unless you started with the same, unless x10 is equal to x20, then you can drop, you can design u to make sure that x1t and x2t will drop to 0 at the same time. For the previous case, if I do have x10 is 10, x2 is x20 is 20, you cannot do it because you can drop, if you drop this one 10 to be 0, you can only drop this one x2 to 10 by the same amount. That's why it's not controllable. Okay, so now because using the definition is a little bit hard to check if a linear system is controllable or not. Now it's important to look at what are the conditions that we can guarantee the system is controllable. So those conditions are typically easier to check, so rather than using the original definition. Okay, so the conditions, there are 3 different conditions to ensure the controllability of, this is a condition to ensure controllability of linear time invariant system. Okay, assuming the dimension of the system, the state is given by n. Okay, so the first condition is to check this matrix called WC matrix, which is integration from 0 to t of e a t minus tau time b transpose time E A transpose T minus tau time D tau. So you sort of can break into two components. This is one part. This is E to the A T minus tau time B. Now this guy is just the transpose of the previous one. So this guy is just the transpose of EA T minus tau B transpose. If you do a transpose, you just switch the order. B transpose goes first, and then E to the A transpose, you do just put the transpose to T directly. So that's how I interpret this WC. You do the integration from 0 to T over tau. Okay, so essentially you get here this W. This is a function of T, because for different T you have different value, right? And what I want to make sure that this WC is non-singular, okay, which means, in other words, it means the determinant of the WC is non-zero. This one should be for all T, right? Then which means this is controllable. First condition is still a little bit hard because you haven't found the integrations, do all the matrix calculus, okay, and also check the determinant is a little bit hard, okay. The second condition is even simpler, which is to compute the matrix C. This is C called Controllability Matrix C, which is constructed by this, which is you put a B as all the columns. B, you could have multiple columns, of course. For B, you put a B here, then you put an A times B, you put an A squared times B until you put an A to the n minus 1 times B. So n is the dimension of the state, okay. So then you check the rank of C to see if the rank is equal to n, okay. If the yes is controllable, if the not is not controllable, okay. The last condition is to check the rank of A minus lambda I and B. Okay, you put this is sort of a matrix, then you put another matrix over here to check the rank, to see if the rank is equal to n for all eigenvalues of A. So here's a lambda is eigen of A. So which means you have to check for, first compute all the eigenvalues of A, then to check if the rank of A minus lambda I, which is one part of this matrix, okay, the vectors, okay, and also you put it for each lambda, and then you put a B with that to check if the rank is equal to n for all, emphasize for all eigenvalues of A, which means you have checked many things. So literally speaking, basically speaking, this one is the easiest way you can check. You just have to compute all this one. Now this one, probably this second and third are sort of equivalent. I probably will going to prefer the second one is for the first approach, and last approach will probably be the last, because you have to check all the eigenvalues, and eigenvalues in some cases could be complex. This can be really complex over here, okay. But the first priority is using the second approach, okay. Now I want to go over a few examples about how to check if a linear time invariant system is controllable or not. Okay, let's start with the first example, which is given by x dot is this matrix 1 0 0 2 is A time x plus 1 1 with B matrix time U, and of course the question is to check its controllability. Okay, now you can use either of the one of three methods, but like I mentioned before, the number 2, the second method, is the simplest one. Okay, so let's now use the simplest one. Let's show you how to do how to construct the matrix C and how to compute the rank. Okay, how to check the rank. So here's the C is built by, you put a B, A to the B, until, of course, you until to the A n minus 1 times B. Now here n is dimension is the size of x, right? Apparently the x has to be 2-dimensional, so this is n equal to 2, this 2-dimensional one. So you put a B, A, B until A n minus 1 is 2 minus 1, 8, 1 times B. So you only have B and AB, you don't have A squared. A squared is not included. So that's why I have B and AB. Okay, so B is just, you put the column over here, 101, okay, and then you compute A times B. What is A times B? Let's compute A times B. A is 1002 times B is 11. So product will be just 10 times 0 0 1 1. So this gives because it's 1. And 0, 2, so 0 times 1 plus 2 times 1 is 2. So this is 1, 2. Okay, don't do the switch order. The order should be, do not switch order. You cannot actually switch the order. Okay, it's not a, this is not this. Okay, it's AB, A square B. Okay, so after doing that, we have to check the rank. The rank of C actually is trying to figure out if it considers a column. You can also do rows. It's the same column to see how many columns are linearly independent. Okay, basically here we only have 2 columns, right? 1, 1, 1, 2. They are linearly independent, right? So the rank is 2. So that means 2 columns of C are linearly independent. If you have 3 columns, they are linearly independent, the rank will be 3, so on and so forth. Okay, now let's take a look at another example. Okay, here we do make a small change. It's almost same as the previous. The only difference is I change this number from 2 to 1. Okay, to see what's happening. Okay, we follow the same approach. We still use the second approach to check the controllability. Okay, so first one we have B. So B is 1, 1. Okay, and A times B is, this is A, this is B. A times B is 1, 0, 0, 1. Times B is 1, 1. So this identity space is you still have 1, 1. It's 1, 1. Okay, now we check the rank of C. Apparently the rows, they are dependent, right? So you only have one vector which is linearly independent. So the rank of C is 1, which is not equal to 2, right? Okay, I haven't finished this previous one. So this is equal to 2, right? Which is equal to the dimension here. The dimension of X is n is 2, which is equal to n. So this is a controllable. Yes. And this one rank is not equal to 2, which is equal to n, so this is not controllable. Okay, so the reason that this is not controllable, you can also write out the reason. So first one, if you write this equation, if I let x to be x1, x2, so I can write down this as 2 equations. So first equation will be x1 dot, which is x1 plus u, and the second equation will be x2 dot, which is x2 plus u. You sort of see the same reason happened before is, yeah, because this, you almost can not change, you cannot change too much, but you cannot, because that's the same, that could cause problems. Okay, so next question is, by looking at this one, the conditions we can check, of course we can check if a system is controllable. The next question is, can we, or how can we, if I give a linear system and which is controllable, my question is, what is a feasible use of T, control input, such that can drive the system from an initial state, it should be x0 to xtf. So assuming you starting time is t and ending at tf. So can we, for example, the question is, if I have starting point here, this is my x0, this is xf, okay, and I know this linear system is already controllable, so I want to really find out this is ut, some ut, such that I can drive the system from x0 to xf. Okay, how do I design this? Because this is a practical problem, right? The first problem, the controllability is relatively easy to check, but this one can be hard. Okay, so the answer to this question is, this is the way how we design the control input, how we could design the control input. The control input given by ut, which is negative b transpose times e to the a transpose tf minus t times the wctf inverse. So wctf inverse is, wc, remember, is defined right over here. This is how we define the wc. Okay, this is the first condition we can use to ensure controllability. Okay, so if we go back, it's WCTF inverse time e to the a time tf time x0. So this is exponential to the power. Okay, you want to make sure this is e to the power and time x0 minus max xf. So you probably can see from here why, because this one you want to find the inverse of that one. So this one WCTF should be invertible. This also somehow explains why the first condition that you can use to check if a system is controllable is WC should be non-singular or invertible. Okay, the next question is why? Okay, why is this? Why this is a valid? Why this is a valid UT? Of course, this has to be for t from 0 to tf. Why this is a valid control input that can drive my state from x0 to xf one time from 0 to tf. Okay. Now to check if this is true, we just have to just use this ut and try to solve for the linear time, because we didn't know what's the original linear time invariant system. We're trying to figure out, hey, what is my xtf? And to verify, yeah, xtf will just give me xtf, that'll be fine. Okay. So here we just use the solution. We just trying to figure out the solution to the linear time invariant system and this control input to see if the state at time tf will be just xf. Okay, to do that, we just recall the solution for the linear time invariant system, which is e to the at time x0 is the initial state plus 0 to t integration from 0 to t of e to the a time t minus tau time b u tau. So that's our solution for the linear time invariant system. We already talked about this one before. So we have to do is we just have to calculate what is my xtf. Okay, and which means I have to replace every t here by tf, tf. Okay, that's it, right? It's all three, right? Then I also replace this u tau by this in this form. Of course, I have to change the tau t to tau. That's what I have to do. Okay, actually, I only have one place, which is this guy has to be changed to tau. The other one, there's no tau involved. Okay. Okay, now let's take a look at the computation. Computing is a little bit nasty to begin with, but again, it becomes simpler later on. Okay, so replace the e to the, because I have to replace everything t has by tf, so this is the eatf time x0. Okay, this is first replaced. The second one is from 0 to tf, so replace the tf to e to the a, replace t by tf tau. Okay, and b over here, so this one u tau, I'm using this one, replace this one, okay, by this one. So it's a negative b tau time e a to the a b tf minus tau minus t. Okay, so this one, I think this one has to be equal to tau over here, and then time wc inverse tf, and this is the same thing as I mentioned before. The wc is defined by here. We just have to replace t by tf, and then we take an inverse of that. Okay, then we keep on doing. So keep on doing this eatf x0. Just copy everything from here. This is not a function of t. Okay, t, not a function of t. Yeah. So replace everything. This is just a copy over here, then d tau. The next we do e to the atf x0. Keep it the same over here, and now we just move this one. So we move this one to the front. So negative to the front. Okay, so minus 0 to tf etf minus tau, and again this one has to be tau. So this is b transpose, because I move the negative to the front, eatf minus tau d tau. Okay, and wc inverse tf, and I move this one outside because this is a function of, if I consider, let's go check the wc inverse tf. Okay, wc inverse tf, let's say wc TF inverse. Okay, so WTF, you replace T by TF. Okay, there's T by TF and TF 10. So you actually have everything by TF. So you actually only have X function only have TF over here, right? So you take an inverse of that. This is not a function. When you consider over here, it's only a function of TF. Okay, essentially. If you go back over here, the reason I can move it out because this is only a function of TF, it's not a function of tau, so I can move it outside. Okay. Also, I have to move to the right hand side because I cannot move to the left. And also keep this one. This one is also not a function of TF only. So this one is function of TF. That's why it's not a function of tau, so I can move it outside. Okay. Now by looking at this one over here, okay, the front one over here, this part, if you compare this one with the definition of WC, okay, WC is this guy, AT minus tau, A transport T minus tau. So we can look at this one. So it's pretty much the same. The only difference is here is this one become TF, this one become TF, and also this TF. Now here in the WC, I have this is T, this is T, and this is T. So this is just WCTF. If you look at this one, okay. So this is just WCTF. Okay. So the nice thing for this one is this is WCTF and this is WCTF inverse. Okay, which means wow, nicely this will be cancelled out, right? Because the time will be identity. Identity you can ignore that. That's why I can simplify quite a bit. Because it's just identity, and I just left with this part. Okay, so and end up having this is e to the ATF x0 minus. This has to keep the minus over here. The minus sign still coming from the previous one, and just put everything over here. So this all whole bunch of stuff become identity. Okay, so this one just e ATF times x0 minus xf. So apparently these two will cancel out, and this negative will cancel out, so we just xtf. So that's the reason why we can have the control input UT design this way, and by calculation, yes, indeed my xtf will be xf. Okay, that's why this is a valid control input that can drive my state from system from x0 to xtf at time tf. Okay. Okay, so that's all for the linear time, the controllability for linear time invariant system.